Okay.
Hello, everybody. Thank you for joining today.
Hello.
We'll be starting very soon. Can you all see my screen?
Yes, sure.
All right, so let's have a little 5-minute discussion before we begin. Context engineering and prompting. Probably you've heard a lot about it before. There's a lot of content around there on the internet. What have you heard about it recently? I'd like to hear your thoughts.
Let me rephrase that. First of all, thank you so much, Sari, for joining us. We're looking forward to your session. Please feel free to open your mic or drop in your answers in the chat box, and let's make this session interactive.
Right, so clarify the way to get best answers from ChatGPT or any other AI. That's generally the premise of it. That's very true. Does anyone else have anything to say? What else do you know about prompt engineering and context engineering? There are so many reels out there
It's
talking
the way
about it.
we communicate with an AI model by giving it a clear instruction or question to get the desired output.
All right.
Okay.
How to get the most optimal answer according to our needs. Prompting is about how to ask. All of these things and what you just said, Ahmad, we all know what prompt engineering is. It's not something that we don't know about. So yeah, it's all very true what all of you are saying. Today we will dive into the framework, the formal framework of prompt engineering and context engineering. We're going to take this knowledge that we already have to the next level. This is a graph showing the growth of in context learning. For example, at zero shot, we have the accuracy increasing with the different types of prompts. We will get into what one shot and few shot mean in a bit. I just wanted to share this with you guys before we begin. So, what are prompts? We already answered this. Prompts constitute instructions and context passed to a language model to achieve a desired task. We have already talked about this. Amazing. So, prompt engineering is the practice of developing and optimizing prompts to efficiently use large language models for a variety of tasks. For example, if you go to ChatGPT, develop Google Docs right now. What would it produce? It would produce something undeterministic. So it wouldn't really converge to an answer. It will try to converge. It will fail to converge because the search space is very large. There are no constraints whatsoever. When I go and say instead, outline the core features for a cloud-based document editor, it's a clear task. There's a clear scope that constricts the context. And my intent is pretty much shown. It's not up to the LLM to interpret what my intent is. My intent is specifically mentioned. This prompt is less likely to diverge, more likely to converge to a deterministic answer. That's a better prompt. So during the session, we will look at different methodologies for optimizing prompts and optimizing context. This is just the surface. Now we are able to differentiate between what a bad prompt looks like and what a good prompt looks like, but we will dive much deeper into this rabbit hole. No free lunch theorem is a rigorous mathematical idea. It's a mathematical idea. What it says is you can't really have a one size fits all algorithm. So if you have a problem, you can solve it in a variety of tasks. You can solve the problem in a variety of ways, and all of these ways probably have different subtle differences in their performance. We're not talking about something like bubble sort or let's say linear search and binary search. This is not the type of thing we're talking about. It's like when you're comparing quicksort and bubble sort. So what's the best algorithm out there to sort a list? Probably you can't have your lunch for free. Probably such an optimal ideal algorithm doesn't exist. There's just a variety of ways we can solve this problem. And so, to reiterate, it is mathematically impossible to design a single general purpose cognitive algorithm, a one-size-fits-all thinking model, or a focus environment that is universally optimal for every possible cognitive task, environmental structure, or knowledge base. So why am I telling you about this? I'm telling you about this because we can just balance our prompts according to this criteria. Prompts are constrained on 4 different pillars: the input and output token sizes, and this directly transfers to costs because, costs directly relate to inputs and output tokens. The expressiveness of language itself, the mental information we're trying to express, and the context windows given by LLMs. So we're going to go back to our no free lunch algorithm principle, and we're going to ask ourselves, is there a best algorithm for optimizing a prompt given these constraints? Probably there is good suggestions. Probably there's good ways to do it. But there's no one best way. A variety of ways. And you as the system designer, you as the AI engineer, you have freedom of choice to tweak around these design choices, organizing these trade-offs until you reach the best method for your current task. So again, to reiterate, prompts are best to be dissected to optimize LLM performance and usage costs. Tasks given to MCPs can thus formally be dissected into a sequence of optimal prompts. So let's pause here for a second. What have we talked about so far? We've talked about how we all somehow know what prompt engineering is about, and that the rabbit hole of prompt engineering really goes too deep. Like just right now, we have seen optimizing prompts can be taken to a mathematical optimization level with no constraints whatsoever. It's really up to design choices, our own design choices. So probably you do this sometimes without even noticing. You write your prompts, expecting or prioritizing certain qualities of the outcome. Maybe you don't have too much time and you can go out of your way with just a little bit of information. It doesn't have to be perfect. Maybe this piece of solution that you're trying to, maybe this code that you're writing needs to be the cleanest code that you have ever written in your life. There's certain things that you can optimize for. Let's say you're at the end of your quota for your free plan, and you don't want to start spending money or waiting for the next, let's say 4 or 5 hours so you can prompt the LLM again. So these constraints, they already guide us to the proper prompting strategies. And thus far, this is something that I think we can all agree on. These constraints, they guide us. They force us to prompt the LLMs in certain ways. What's going to happen next is we're going to formalize this concept. We're going to elaborate and expand upon this concept. We have it among ourselves right now. We have this concept now. That prompts should be balanced. We don't know how yet. We have talked about examples of how we can balance prompts, certain use cases. Now let's dive right into it. Prompt engineering. As I was saying, there's still no widely recognized formal algorithm that dissects tasks, which takes all these optimization constraint factors into consideration. But there are general guidelines that we can benefit from already. The collection of these guidelines are what is generally meant by prompt engineering. It's a collection of these guidelines. Why do we use prompt engineering? It helps us research, discover, and develop advancements in society. It helps us in testing and evaluating the limitations of LLMs. It also unlocks the potential of LLMs for us. So a prompt consists of clear instructions, a context, which is its input data, and the output indication. The output indication is something like an example of how you want the output to look like. There are constraints on the output that the LLM should generate, so it wouldn't diverge too much. So going back to the example of Google Docs and outlining the core features of cloud-based document editors, you see how there are many possible answers for developing a Google Docs. But then when you give it an output guardrail, suddenly it's able to filter out some answers and only keep plausible answers. So just by specifying the output indication, you're already constricting the prompt answers, which is good. You can take it way more than that. Here are some general tips to avoid when prompting. You can't overload it with too much irrelevant information. You can be ambiguous because you're leaving all the design choices for the LLM, which is not ideal. It wouldn't know how to design these choices itself. And you can't overcomplicate things for it with lots of complex, like meaninglessly complex phrases. Like, complex phrases might exist, and in certain specific scenarios, you might need to use technical phrases, complex phrases and jargon. But some of the times, it's better to avoid them if you can. So simplicity is your friend. And that goes directly back to the fact that prompts are constrained by the expressiveness of language itself. See, when you have an idea, or in other words, mental information that you want to express, you can express it in many ways using the same language. So what's the simplest way? What's the most complex way? Probably you've heard some people dabble on and on and on for minutes trying to explain one idea. And then someone else comes. They can restate the same idea in 1 or 2 sentences. So word choice is very important. What's simple for us is also simple for LLMs. This is a property of language itself. It's not a property for AI and LLMs and those sorts of things. It's a property of language. We must be mindful of how we're communicating our ideas. So as we were saying, conciseness is really nice. Now, there are some hyperparameters that you can tune for deployed LLMs. So you're not training LLMs from scratch. You have an LLM and you want to deploy it, and you can tune it for hyperparameters. When you do that, same prompts may result in different outputs. For example, you have temperature hyperparameter. If it's too low, then it's only going to use the provided context. And when the temperature is very high, it's more likely to spit out some random responses. So at low temperature might, for example, result in fresh coffee every day. Whereas a high temperature may result in a response like brew dreams in every cup sip to sunrise. So temperature defines how random the next token the LLM is trying to predict. It gives it a threshold of randomness. And when you give it too much free will, which is high temperature, you might expect some really creative outputs. But maybe You don't want to be creative when you're trying to book a hotel room. So if you're deploying an LLM in, for example, a hotel management app, you can't really get creative and say, well, when the afternoon comes and the birds go to their nests, there's a room that overviews the sunset and the sea, which you can book in this hotel. You must be very specific and say, well, this room, 130C at floor 1, is available for booking from 3 p.m. on a specific day till, for example, the next week. This is the difference between low temperature and high temperature responses. Another hyperparameter is top P. Top P stands for top probabilities. Probabilities of what? Probabilities of the LLM's next tokens. So let's say the LLM generated a response. It doesn't just want to give it to you yet. We want to take the output tokens and filter them via importance. What's the probability that this token is important? What's the probability that the next token is important? What's the probability that this word is relevant or irrelevant, or highly important? Now we're at the phase after temperature tuning. We're at the stage where we have already developed our output. Now we're just selecting what output we want to relay to the user. The probability of 0 will give you no response whatsoever. Because when you try to sum up the probabilities of the tokens to 0, you simply get nothing. Now, usually, the parameter top P is set to 1.0, which is the default value. 1.0 is no filtering whatsoever. The LLM output is given to you just like it is, without any change. When you tune it, if you want to cut off on the output size, the output tokens, and thus cut costs, you may want to filter it according to top probabilities of 0.9. So you want to take the output of the LLM and keep adding on probabilities of importance up till they reach 0.9. Now you have a more curated response. Now there are some caveats to that, where combinatorics are actually very hard. In this case, you will probably need a higher level of abstraction with, for example, reinforcement learning, but the strategy is still good enough. Here are some general prompt engineering techniques that you can use. Few shot. You begin by saying, translate hello to Spanish. It says hola. It gives you the answer hola. Then you will be able to directly ask it to translate bread to French. That will say baguette. So you're going from one similar prompt to another similar prompt. Chain of thought. You ask the LLM, if I have 3 apples and buy 2 more, that's 3 plus 5. Now, taking this step by step, now if I have 3 tons of apples and 2 tons of apples, that's the total tons that I have on my ship that I'm shipping from, let's say, Europe to Tripoli. It will tell you 5 tons. Obviously, this is a very simple example, but the chain of thoughts still remains. Self-consistency let's say generate 5 different reasoning paths. You want to search for, okay, well, I have different design choices. I have a huge design matrix, and I want to find out which options I can choose. And you go ahead and you give it 5 of the possible paths that you can take in this design matrix. And let's say 4 of them consistently end up with an answer like 5 apples, or doesn't need to be 5 apples. It's just generic output. So when there's consistency in the outputs, different reasoning paths, well, you know that this is probably the correct answer. It's like when you go and you ask the same questions to 3 or 4 different LLMs and you get generally the same outcomes, you usually ignore the diverged outputs. Your brain automatically ignores them. Knowledge generation. Knowledge generation, by the way, directly leads to RAG, retrieval-augmented generation. It's the predecessor. So let's say you begin and ask, before you go ahead and ask LLM about something in your lecture, for example, you're studying biology, you want to start on equal terms. And let's say before answering anything, just generate known facts about photosynthesis. Let us say plants convert sunlight into energy. This will give you a platform, a foundation where you can go up from. So then you can ask more about it and you can go more in depth. But now we have established the base knowledge that you want the LLM to base everything on. There's something also very nice called React. It's something for you to take into consideration. So you would think, oh, well, I need to know what the current population of Paris is for some reason. I want to know what the current population of Paris is. So you don't go ahead and tell the LLM, oh, I need the current population of Paris right now. Please just give it to me. You click on search and you type Paris population. Maybe you can also say search Paris population 2026. Will give you an accurate result. So an LLM is a powerful but isolated brain, limited by its finite context window. You cannot solve this by writing better prompts. A good prompt still depends on what the model knows. The model can answer without real understanding. Prompts cannot add missing background information. Same prompt can give different answers. Prompts do not control what the model pays attention to. Prompts cannot fix outdated or incomplete knowledge. And for complex tasks, prompts are not enough by themselves. Whoa, what just happened? We just listed like 7 caveats of prompt engineering. And there's probably 1,000 more. So we need a framework. We need a systematic framework to avoid these caveats. Instead of only changing the prompt, we need to systematically change the context that the model is exposed to. This is context engineering. The core premise of context engineering is that we must build an intelligent system around the model to feed it the right information at the right time. Components of context engineering include, we have first of all the agent. It's the orchestrator. They manage all the other components that we're about to list next. First component is query augmentation. This is just like the interpreter. You know, when you want to compile your code, there's first of all an interpreter that goes ahead line by line and interprets the written strings into executable tokens. It gives them tokens. Similarly, here we have query augmentation for prompts. LLMs probably need this when they are in an agentic framework. So they need to interpret what the prompt is saying into actionable intent. So it transforms vague user requests into precise machine-ready instructions, not because the user instruction was vague, but because the prompt can literally mean anything. Retrieval is the bridge. It connects the LLM to specific document, databases, or the likes. Via RAG, retrieval-augmented generation. I've already mentioned this. The most critical design choice of RAG is chunking strategy. This is when you want to optimize how you want to take inputs from a variety of PDFs. So, for example, if you have 2,000 PDFs, you can just take them all, you chunk them in a certain chunking strategy. For example, you can chunk by closest to relevance. It's similar to top P that we talked about earlier. So again, the agent is orchestrating all of these things. Now we have discussed query augmentation and retrieval. What else is there? Prompting techniques, we have already talked about these. They are the instructions that the LLM will abide by. We have chain of thought, few shot, etc., etc. And they give guidance to the LLM reasoning. As we were saying, the query interprets the prompt and casts this interpretation into certain prompting methods like chain of thought, few shot, and so on and so on. So now we have a sequence of interpreted prompts. To take action, we must use tools. So tools are the actuators. They allow LLMs to take real action, like API calls, web search, using something called the Model Context Protocol, which is a software architecture specifically for context engineering. Model Context Protocol is what allows Cursor and GitHub Copilot to exist in the first place. Sometimes you might need to retrieve some information to do these tools. Of course, this is all going to be automated. These are the components of context engineering framework. It's a formal framework altogether. All you do is prompt the AI. You never go to ChatGPT and tell it to, for example, choose to use this tool. You might see it, for example, searching sometimes on its own. You have never asked it to search. So it's all happening internally. The AI engineers have developed this functionality with context engineering. And lastly, this is quite important, memory. It's the history of the chat. For you to be able to keep on going in the same chat. So this gives system state across interactions, combining short-term context, long-term storage, working memory for multi-step tasks, or just multi-step prompting. This allows for dissecting prompts into multiple steps. So imagine all of these techniques taking into consideration. Now let's revisit the constraints of prompts. I have the context windows, which is the amount of tokens that are analyzed at a single forward pass in the neural network. And now you're saying, okay, well, I want to optimize how much I'm going to be inputting and outputting. I can optimize the expressiveness of the prompts, and maybe the only thing that you still cannot really automate is the mental information to express. This is the only thing that still yet still doesn't have any application. They can optimize it in the literature. So again, I'm going to go back and say, well, with this context engineering protocol, we kind of can observe systematically how we can systematically balance our prompts to optimize the performance and usage. That's very nice. It's very, very nice. But hold up. Before we go any further, it's very, very, very important to mention safety in context engineering. This is the 7th pillar of context engineering. We have context safety. It's the guardrails. It ensures fairness, privacy, security, and alignment across all components. Context safety is a very, very, very underrated pillar of good prompting practices. With the rise of AI ethics, recognition from regulatory bodies like the GDPR, malicious outputs of LLMs no longer go undernoted. Recently, it's been revealed that AI can be used for harm just as well as it's used for goodness, even when the intent is good. Subtle malfunctions may lead to imminent disasters. So you don't really need to intend to do any harm. It's just malfunctions, and it does harm. Aside from malfunctioning and stuff like that, let me give you an example, something concrete that really, really, really touches upon how important and how rigorous safety is in context engineering. Medical data. IRB. Wait, someone's raising up their hands. Never mind. So, medical data with an IRB certificate or other NDA signed data, for example, cannot be leaked. You cannot leak it anywhere. It has to be private. It has to be. Even when you prompt the AI with de-identified prompts, with de-identified data, with enough context, LLMs can reconstruct the data source. But very rare condition, even with no direct name or other identification is revealed. MRI images of the brain can reconstruct facial features. Okay, this is obviously something that LLMs cannot do, but at least currently, with no MRI tool. Like if you're using an MCP server, okay, yes, maybe you have an MRI to facial feature pipeline. The LLM might just reconstruct the face of the de-identified patient. So if you're into medical projects, if you're a medical student, if you're being involved in medical applications, and you have signed an IRB clearance, or for example, an NDA with a company or something like that, be very careful with the context that you're giving. A very rare condition, with a geolocation, with an age limit, with all of these things, even if you don't state the name, even if you don't state the institution they're at, the LLM will still be able to identify the patient. And you will have leaked data into whatever system that you're using. It doesn't have to be OpenAI or whatever. Maybe this output shouldn't be revealed to clients that are using your LLM that's fine-tuned by you and hosted by you. Another thing, this is something that I've personally worked on in my research, was membership inference attacks. There are a family of mathematical algorithms that reconstruct training data. So it's training data. It's literally being reconstructed from careful analysis of inputs and outputs, small deviations of agentic systems. So we go on, for example, we go to Nano Banana, and I ask it to draw something. I ask it to draw an image. And I change the prompt slightly. And I see the next image. And then I keep asking it the same prompt over and over again for 100 times. And I look at the dispersion of images. This output of 100 similar images will indicate an interpolated training data. That's it. Just from prompting, you can reconstruct the training data. So how can you not leak the training data? This is something that the GDPR is very crazy on very recently, and we absolutely need solutions for these things. As you might imagine, this rabbit hole goes on and on. There are lots of keywords beyond medical data, beyond NDAs, beyond membership inference. Like there are many keywords to sit here, like algorithmic bias, for example, in jails, what they use in jails and the law system, cultural skew, and LLM personas, because LLMs reflect the culture of their training facility. Red teaming, adversarial testing, data provenance, data minimization, explainability, and on and on and on. So this is a very active area in industry and research. No matter who you are, you can contribute to this. It's very much needed. So context engineering is a holistic framework for dissecting complex tasks into a series of optimized smaller tasks for agentic AI systems. Even if it is not a mathematically optimal free-lunch algorithm per se, to manage the trade-offs of prompting, like like precision versus richness, like cost versus performance. The presence of context engineering, like the fact that it is a robust system that everyone is using right now, suggests that there are other algorithms other than context engineering as a framework. So context engineering as a framework, and I'm suggesting there are other algorithms for task optimization for agentic AI. And it may perform on par with context engineering, because this is what the no free lunch theorem states. When you have different ways of solving a problem, maybe when you consider all the possible applications, all the possible examples, and you average out all the performances, they almost nearly all converge. So now we have context engineering, and it's our best bet for optimizing LLM systems. So I have finished. Thank you all for attending. Please check out this website called skills.sh. If you have any questions, please raise your hand. I'm very open to discussions. We still have, I think, 10 minutes.
Thank you so much, Sari, for the very insightful and enrichful session. So we managed to go a bit over what prompt engineering is, then what context engineering is, and we had the chance to reflect on them from a research perspective with Sari. Moving forward, in the upcoming bootcamp in February, more announcements later on during the last session for today at 7 p.m. We're gonna be reusing some information and some of the skills that Sari tackled during this session, and we're gonna be applying them hands-on, so you could have the chance to experiment. Meanwhile, I recommend you check out this website, which is skills.sh. You can download this package and reuse skills in building your own agents with Claude Code. If you have any questions, feel free to drop them in the chat box or just raise your hand. Thank you, Sari.
Thank you, Sarah, for having me. Thank you all for listening. Ahmed, you were raising your hand. Do you have anything to share? Anybody else? الله يعافيك يا مهدي. It seems like nobody has any questions.
So
Thank you for attending.
Thank you so much, Sari, for the great session. I believe this is a wrap for the context and prompt engineering session. We'll see you guys soon in the upcoming session in a few.